Good day everyone, I'm RUBESHNAIR KUMARAN, metric number B0122100085, and today I'm going to talk about the electrical testament performance with EASY68K, and my teammates JISHNU, RUBEN, KALITHASS, Nahvin, SEKARAN, and NITHYA, SIVARAMAN, and I will thanks to my lecturer first of all, Dr. TARMIZI bin IZZUDDIN, for helping me through all this subject. And then we go for the introduction for a quick. What is a microprocessor? A microprocessor is an integrated circuit that contains the functions of a central processing of a unit, which we call a CPU, in a single chip. Key function is execute the instruction and perform calculations and control peripheral devices. How microprocessor works: fetch, decode, execute cycle. This is the main thing, and this is being listed in the slide as well. And then the main objective of this project is to simulate and analyze the performance of an electrical fan using an app that we call software is EASY68K and an emulator for the Motorola 68000 microprocessor. So main focus of this is control fan speed, implement speed regulation, and performance metrics, as how it works and how it's control the speeds with the LED lights and also the displays that which shows what the speed is. So it's the algorithm steps that we're using: read user input and display with the current speed status, and then we can use the switches to control the motor signal to match the desired speed. So this is the objective. So next is list of components that we use is Motorola 68K, 8 segment LED switches and switches. So I will pass the next slide to my friend Nithya.
Hi everyone, my name is NITHYA. Let me explain about the coding. First, we have declared all the hardware that we use for the simulation. We use EQU command, which is used to define the memories for the hardware. We use switch, LED, and also 7-segment display to show the output of the system. Let's move to the initial condition of the system. ORG XR100, which is the starting memory of the system. Move.b immediate XR1, D0 means it will move the data 1 to data register 0. Move.w immediate XR1, D1 seems to the D2, D3, D4, D5 and D6. So it means we define all the initial data for the data registers. We use D0 for LED and D1 to D6 we use for the switches. Next, we move to the main part of this coding, which is the decision making part in this coding. Move.b D0, LED, which is it will move the data from D0 to LED. We also use CMP compare.b switch, D1 BEQ branch if equal startup. It means it will compare the switch with the D1 values. If both the values are same, it will jump to the startup routine. That's the job of the BEQ. This is the same concept that we use for all the switches D2, D3, D4, D5, D6, and we have each subroutine for each switch like D2 speed 1, D3 speed 2, like that. We use BRA main command, which is loop to the main, so it will loop continuously. Let's move to the startup. So this is the code that we do for the 7-segment display. So when the startup process happen, the display will show this. Then we use the BRA main command to make loop to the main. Let's refer to the speed 1, ROL.b immediate 1 D0. This means the 1 data will loop to the D1, rotate left continuously. Move.b D0, LED. It will move the D0 data to LED. Then BSR command used for call for subroutine fast. So this is the command that we do for the 7-segment display. It will display when the speed 1 it's happening, it will show speed 1. BRA, it will back the loop go to the main. This is the same concept that we do for speed 2, speed 3, speed 4 and also stop. But the difference is for the BSR in speed 2 it will call for the faster, the speed 3 will call for fastest, speed 4 super fast, and the stop will go for speed D0. So the display in the 7-second display code also different. For the speed 2 it will go for speed 2, speed 3 and speed 4. For the stop it will go for stop. After that it will go back to the main because we use the BSR command here. That's all from me. Let me pass to my friend Nahvin.
Thank you, Nithya. Let me introduce myself. My name is Nahvin Arusekaran and my registration number is V0122101117. I am going to explain about the last part of our coding and demonstrate the simulation. Each subroutine essentially performs the same sequence of operations. By using this subroutine, we can simulate different fan speed by introducing varying delays in our program. Each delay subroutine in our coding, such as speed 0, fast, faster, fastest, and super fast, corresponds to a different fan speed from slowest to fastest. Now, let's take a closer look at the delay subroutines used in our assembly program. First, for the speed 0 subroutine, move.l #s 10,000 D7. This instruction loads the long value $10,000 into register D7. Then, wait 0. This is a label marking the start of the delay loop. After that, subi.w #1 D7. This instruction subtracts the immediate value from the lower word of D7. BNE wait 0. This instruction means branch if not equal. It checks the result of the previous operation. If the result is not 0, meaning D7 is not 0, it jumps back to the wait 0 label, creating a loop. RTS. This instruction stands for return from subroutine, which exits the subroutine and returns to the main program flow. This loop will create a significant delay, which corresponds to the speed 0 or the slowest fan speed. The following subroutine perform the same sequence of operations, except the move instruction. The speed will become more faster every time the immediate hexadecimal value changes to a smaller value. For example, the second subroutine, which is fast. For this subroutine, if you see $sign $7,000, the speed will change to a faster. This is how the subroutine works for all the upcoming case. Now, let's see how this works in the EASY68K simulator. First of all, we have to open the EASY68K and load the assembly code. Then assemble the code to ensure there are no syntax errors. After that, open the simulator by click View and Hardware. In the simulator, we have the 7-segment LED display, switches, and LED lights. Ensure that the memory address match those defined in the code. Then, we have to start the simulation by clicking Run. Initially, the display shows the start pattern. When I turn on the first switch, it sets the fan to speed 1 and the LED lights blink fast. When I turn on the second switch, it sets the fan to speed 2. The LED lights blink faster. When I turn on the third switch, it sets fan to speed 3. The LED lights blinks faster. After that, when I set fan to speed 4, the LED lights blink super fast. Finally, when I turn on the switch 5, it will stop the fan. That's all from me. I pass the next part to JISHNU. Thank you.
Thank you, Nahvin. Now I'm going to present about the discussion. So this is an overview of our fan speed control system, which operate using EASY68K microprocessor, effectively managing speed based and user input from push buttons with visual feedback provided by LEDs and a 7-segment display. The system initialized by setting default values and entering a main loop where it continuously checks for button presses to adjust the display to show the current speed, ranging from startup to various speed levels and a stop state. Each speed level is associated with a specific delay to simulate different fan speed, and the program ensures real-time responsiveness and accurate control through well-defined subroutines. So now I'm gonna present about the conclusion and recommendation for our system. So in conclusion, our speed control system has successfully demonstrated efficient and effective management of fan speed using EASY68K microprocessor. The system provides a user-friendly interface with clear visual feedback through LEDs and a 7-segment display. Overall, it delivers reliable performance with robust and real-time response to user inputs. So now for the recommendation. To improve the fan speed control system, we recommend to use advanced input methods like rotary encoders or touch sensors and sophisticated control algorithms. Integrate temperature and humidity sensors for automatic speed adjustment and add motion and light sensors for room occupancy and ambient light. For energy efficiency, use sleep modes and low power microcontrollers and LEDs. Overall, the fan speed control system not only meets its current objective, but also has great potential for further enhancement and improvement. By integrating advanced input methods, additional sensors, and focusing on energy efficiency, the system can become even more user-friendly. Thank you. That's all from us.